I'm YingRen from National Ilan University, Taiwan. It's my great honor to present this GAN-based cyclostationary noise generator for narrowband powerline communication systems. At the end of 2021, part of this presentation has been published in this paper. If you are interested in my talk, you can see this paper for more information. Narrowband powerline communication systems is one of the possible last-mile solutions for smart metering. However, the powerline infrastructure is designed for delivered power rather than signals. Many impairments are needed to be conquered, such as the multipath effect of the channel and the diverse noise component. One of the prerequisites for designing a high-performance transceiver is the understanding of the additive noise. As you can see in this figure, it has been pointed out that there are 5 main additive noises in the powerline communications. For the narrowband powerline communication systems, the dominant one is called cyclostationary impulsive noise, and it is a periodic impulsive noise synchronous to the mains frequency. However, we know the Greenfield algorithm is a lossy inversion, so we propose a phase-length spec-GAN approach. And in our approach, we not only use the amplitude spectrum, but also use the phase spectrum. So at the end of the training, we don't use a Greenfield algorithm to do the inverse short-time Fourier transform to get the generated data. So now we use numerical analysis to see the effectiveness of our proposed method. The time domain data are generated by a fresh filter, and this approach can be found in this paper that has been published in 2020 in IEEE Communication Letter. So we assume this is our real data. As you can see, the third row is the time domain trace that generated by the spec-GAN, and the last row is the time domain trace generated by our phase-length spec-GAN. So I believe you can see that our model can generate the time domain samples that is much similar than the real one. We can use another average magnitude spectrum and the cumulative errors like this. The x-axis is frequency, y-axis is the magnitude spectrum. So you can see that our proposed method and the real one is much close. However, the average magnitude spectrum has a large deviation from the real one. So as you can see the cumulative error, our proposed method have about 25 dB gains. Lastly, we use the Freiheit inception distance FID values to compare the accuracy and the diversity. The FID value can be calculated using the mean vector and the covariance matrix, and the lower value means the better accuracy and the higher diversity. So you can see the right column. We use the principal component analysis and plot the most two significant component 1 and component 2, to visualize the result. The red one is the real one, and the blue one is our proposed phase-length spec-GAN. However, you can see the traditional spec-GAN, due to use the lossy Greenfield algorithm, so the result is not so good. This is all my presentation. Thank you for your listening.